years. Acha, Asif, I just saw your message over here. I'll check it out on Messenger later. I'll check it out. Check out. Acha. So about the law of conservation of sorry, about the idea of energy resources, the primary thing that I wanted you to is to remember and understand that except for the fossil fuel and the nuclear fuel, every other forms of energy, except for fossil, sorry, not fossil fuel, except for the heat energy of the Earth's own, which is called the geothermal energy, and nuclear fuel. Nuclear fuel is basically Earth's atoms, radioactive atoms, broken into pieces to liberate energy from inside. Except for these two sources, all the other sources can be considered to be are somehow attributed to uh, sun. So these energies are made available to us because of sun. So fossil fuel is actually very simple because the idea of fossil fuel is that the alive trees and animals uh, underwent decomposition and they converted into hydrocarbon over millions of years, thousands of years, and eventually that conversion happened under the effect of temperature and pressure, and so we have now decomposed or broken hydrocarbon molecules, methane, ethane, propane, ethene, all those stuffs, which you can burn to make carbon dioxide and H2O. So initially there was CO2 and H2O in the atmosphere. The photosynthesis happened by encapsulating the light energy available from the sun. So it is important that the energy that is actually stored within the fossil fuel that actually came from the sun, because the sun was providing the earth energy back then. The photosynthesis of the plants could happen. That's how they stored the energy. Either those plants directly died and converted into fossil fuel later on, or maybe some of those plants were eaten by the animals, and that was converted to fossil fuel. So either way, it essentially came from the sun. So wind energy is, on the other hand, is actually a pretty very important thing. Wind energy is a very useful energy form for us, because whenever we say wind energy, we essentially mean the energy of the wind whenever it is traveling from one place to another place at a significant speed, preferably. So wind is basically, air is a gaseous medium, which means it has mass, and by wind energy, the benefit that we have, that we are having moving mass, which readily has kinetic energy within itself. So the first available form from the resource or of wind energy is the kinetic energy of the wind. So we are directly having the kinetic energy of the wind. We don't have to go any other previous form. If you wonder why am I saying about any other previous form, because you should remember the flow diagram that we discussed last class, that for all the cases of the flow diagrams or energy flow diagrams, basically at the end we want electrical output. That's the important bit. So we want electric energy, at the end. This is our end product expectation. We want to make this out of whatever energy form that we have available to us, and this usually comes from kinetic energy of some fluid, and that conversion is made by a device, and the name of this device is generator. So we feed kinetic energy into the generator converts that kinetic energy into electrical energy, and that kinetic energy could be converted by other devices. For example, whenever we had heat energy, we had a boiler, we had a turbine, so there was constant conversion. If you consider the geothermal energy or solar thermal plants, where we can concentrate the heat of the sun. I'm going to show you some videos into the classes as well, where we can actually see that there are multiple different ways we can actually concentrate the heat of the sun. It's pretty interesting. Not very popular yet, because the photovoltaic or the PV cell, the solar cell, which converts sun's light energy directly into electricity, has become more popular. So solar heating is not a very popular product or project, but maybe it will flourish later in the world. Maybe, I don't know. The point that I'm trying to make is that the immediate earlier form of the electrical energy is the kinetic energy of some fluid, kinetic energy of some object, maybe liquid or gas or solid. So in the wind energy case, this kinetic energy is our available form, which means we only need to convert somehow, capture this kinetic energy of the wind and convert that into some sort of energy. So this is the beauty of it. So the way it works is that, why does the wind happen on Earth's surface to begin with? Now here's the thing that I need to understand. If I am trying to show you the shape of the sun in appropriate scale, I would be far off within this part because I don't have a measurement mechanism on this MS Paint. But what I need to understand that sun, yes.
Sir, is the immediate form of energy before electrical energy always kinetic energy of some fluid?
Not always. Whenever we are using generator, in those cases, we are not going to use generator in all cases. For most cases, we are going to use generator, but there can be also, we can also directly convert light into electrical by using the PV cells or photovoltaic cells, which we have on our calculator in large panels and on rooftops and such. Usually, this is the most popular one. Let's say all the energy conversion that we have, all the electricity that we have available to in our grid in the entire world, let's say about maybe 85% of the energies are created in this mechanism. Some sort of kinetic energy is fed into the generator rotates within a coil, and then that produces the electrical energy. About 80-85% or maybe more. And directly light converted to electrical energy is actually pretty small. And we human beings are trying, or we should try, let me put it that way, to achieve this better, because this causes less pollution.
Yes, sir.
Beautiful. So the point I was trying to get is that sun is practically really far away from us. So let's say if you consider that this is the position of the sun and this is the position of the earth, figure not drawn to scale, compared to the curvature of the earth's surface, the distance is extremely large. The reason I'm telling you this is that if I try to represent the surface of the earth by a sphere, let's say this is earth, okay, and now let's say sun's rays are coming from here. So let's say this is one ray of sun. So this is coming like this. For the sake of simplicity, I can practically represent the entire sun's ray coming to us as parallel rays. Although they might not be perfectly parallel, there might be some angles between them, but we can show them to be parallel. It is logically acceptable because the distance between the earth and the sun is really, really large. So the incoming rays are parallel, and the earth's surface is curved. Now, this is the part that I want you to understand, kids. What I'm going to show you over here is a very basic idea of intensity distribution. You don't have to know these terms; these are a bit mouthful, but it's pretty simple. Here's the deal that I want you to understand. Let's say, let me give you a very simple example so that you can understand what I am talking about. Let's say you have a shower head over here, which is producing droplets of water, which are all falling down. So they're all falling down. Consider this. You have a piece of plastic, let's say a piece of rectangular plastic. Let's say that rectangular plastic piece has a shape like this. So I'm trying to show you a bit of a three-dimensional shape so that it's understandable for you. Now, think about it. If I take this plastic sheet and if I place it over here, this is how the plastic sheet looks like. But just for the sake of easier understanding, I'm going to try to attempt a 2D figure over here. So I'm going to represent this plastic sheet of paper, rectangular plastic sheet of paper, as a line, as a simple line. So what I'm trying to show you is that, let me just copy this because I'll be reusing this thing multiple times. Let's put it there. So if I put this plastic sheet under this flowing water horizontally, like this, maybe, let's say this is the total length of the plastic sheet and I'm having it right over here. So yeah, so then I'll be blocking the water droplets which will be hitting this plastic sheet. So I'll be receiving a certain number of water droplets per second. So technically speaking, the water will be flowing on the two sides of the thing, so I can rub off the in between part. This is the region where the water droplets would not be coming down. So this part would be free of water particles, not essentially dry because water was falling earlier, but here I would not have any water droplets. Similarly applicable for the light as well. If this is light and you place something in the path of the light, you produce a shadow region underneath that place where you have blocking the light. That same surface, try to understand, so this will be receiving a certain number of water droplets per second. In another scenario, if we now place the same surface of the same length, but we place it at some angle, let's say something like this. So you have the same length, but you are just putting it at some angle. Essentially, you'll be blocking fewer water particles now, because now these objects, because the orientation of the object, less water particles would be hitting over here, because you will now cover a much smaller fraction of the falling water, because vertically you are blocking a less amount of space. If I make it more angular, for example, let's say at some point, if I start to make this hold this plastic piece nearly vertically along the water flow path of the water, if I keep this thing like this, maybe I'll be dropping very few. I'll be actually blocking very few water droplets in the flow path of the water, because only the borderline of this plastic sheet, let's say the thickness, very small thickness of this plastic sheet, would be responsible to block the water. All the other water droplets will be falling from on the left and right side. It is the same piece of surface, but because of its orientation, it will receive a different number of water droplets because of its angle. The same thing is applicable for the light as well. If this was, other than considering this as a light shower head, if this was a light source, which is, let's say there are multiple LEDs over here and this space shining light through here falling downwards. If this was a light source and this was an opaque object, a non-transparent object, and if you held it like this, you're gonna get the biggest of the shadows, which means in this case, right over here, we're gonna have a huge amount of light energy falling. So the amount of energy received over this space would be really large, because it will be blocking a good amount of area of light as is in the path of the light. Whenever we're going to make it some angle, the amount of light would be somewhat smaller. Whenever we're going to place it vertically, the amount of light would theoretically become zero, although it cannot be perfectly zero, because some light would be actually blocked right over at this edge or the thickness part of this thing. So it will be very small. Let's say it's approximately zero. So whenever we are making an angle, the same amount of surface will be receiving less amount of light. And for the sun, it's not only light, because sun provides us light and heat both. So it is equally applicable for the heat energy as well. Why is this interesting? I mean, why am I trying to badger your head with this angle information? I mean, what is the point? What is my end game? The idea is that whenever sun's energy fall over here, the location which receives vertical sun ray, for example, let's say in this case the horizontal rays are coming. So let's say in this equator region, the sun's rays are falling pretty vertically. So this is right over here. It is noon. Noon means it is noon. It's 12:00 p.m. or somewhere around or 1 p.m. something like that. Sun's rays falling really vertically. But if you consider right over here, let's say right over here, the sun's rays are falling at some angle. So if you consider the same amount of sun's energy, let's say the same thickness of the heat beam that is receiving to Earth, let's say this amount of beam, this is gonna reach up on this on this amount of surface. So this amount of heat energy of this size of, let's say, a cylinder or rectangular shape, this is gonna heat up this amount of space. But if you take this exact shape and try to get how much this heat would be distributed over here, you'll see that this same amount of energy would be distributed to on a very larger area for this space. For example, if I now try to extend these arms, have a look. So for this case where it is noon, this is the vertical falling of the energy. So in this case, the energy is really concentrated. this amount of energy is constant on this small piece of area. But whenever it is dawn or it is dusk, this energy, the same amount of energy for the same thickness of the material, this is just a hypothetical amount just to make my point. This will be distributed over a large area. This is why we would have comfortable temperature in dawn and dusk typically. So because the energy is distributed over here, this part of the land will not be heated as fiercely as this part of the land. So the energy absorption by the mass of the land would be much less fierce right over here. It will be really fierce right over here. Sorry, ulta bose. It will be less fierce over here. It will be really fierce over here, which means in terms of temperature, this part will have a higher temperature. Compared to that, this region will have a lower temperature. এই আইডিয়াটা বুঝা গেছে কিনা? This is because of the, I mean, this is the example that I'm trying to show you, irrespective of the presence of the cloud, clear sky. Even if clouds are not there, clouds also play a very large role. I'm going to talk about the clouds just after this part. But the idea of the curvature of the earth that is causing for different location of the earth to be heated up differently. Some places are experiencing high temperature, some places are experiencing lower temperature just because of the curvature of the earth. এই লজিকটা বুঝা গেছে কিনা? Kids, questions? Anyone? I'll take questions now. Hello.
জি স্যার।
আচ্ছা, I'm assuming যে এটা বুঝা গেছে। ওকে, সো এটা একটা রিজন। সো এখন যে জিনিসটা হবে, এই তোমাদেরকে যদি আমি অফিসিয়ালি এখনো কনভেকশন প্রসেস পড়াই নাই, বাট মেনি অফ ইউ মাইট হ্যাভ কাম অ্যাক্রস দ্য আইডিয়া অফ ল্যান্ড ব্রিজেস এন্ড সি ব্রিজেস in your lower classes 6, 7, 8 geography classes or normal science classes. The idea is that because this part of the land would be really hot, so air would be going up in this case means away from the earth at a really high rate. Compared to that, this air is cooler, so to fill up that gap, colder air or cooler air would be flowing in. This is basically what we call convection current. So location where there is midday, those locations would in those locations the air be going vertically up, so we would not be sensing it much because we human beings are not so tall to understand that upward flow of air. But this will be highly experienced by birds which use the upgoing air for their flight. For example, what is it called? Vulture to na egulo jani ki bole? Hawks. Yeah, hawks. They use the upward current of the air to gain height, so that they would have to spend less energy by flapping their wings. So they do that. So this is going to happen. So in the midday, on midday, these locations energy is air is going to start to flow upwards, and from the cooler region, the air is going to flow horizontally. This is basically one of the primary reasons why we have airflow on Earth's surface. If this uneven heating was not happening, for example, let's say if the Earth was not like a round shape that it is, nearly round shape that it is, if Earth was like a cube, then we would never have this. We would almost never have this, because if it was like a rectangular shape or cuboid shape, then one entire surface would always experience the same rate of heating. I mean, whenever it will be inclined, the rate of heating would be decreasing all through the surface. So either the entire surface is receiving high heat or the entire surface is receiving low heat. So the possibility for airflow would be only around the border lines or where two surfaces merge. Only in those locations could we possibly have some heating effect, but we are not going to have large significant airflow across those surfaces. Because the Earth is curved in the way it is, we have this uneven heating. This is the term, uneven heating of the sun's rays, and as a result, we have different temperature in different places, and hot air goes up in the hot places, cold air from the cooler places flow into the hot places to fill up that void. Convection current happens, and that's how this happens. So this is one part. The other part that is important is for the clouds. Clouds are pretty simple. Yeah, this part that I'm trying to show you is basically for a much larger scale for what happens on the Earth. তোমাদের স্ক্রিন কি ফ্লিকার করতেছে by any chance, or are we seeing a continuous stream?
Continuous stream.
My screen is continuously flickering. I'm not sure why is it happening. Is this a graphics card problem?
Sir, it could be because of your monitor, maybe.
Well, my monitor, my older monitor got busted last week, so I got a new monitor, which is not essentially brand new, but I just had another monitor which I used to use as TV, so I plugged it up. Same model, same hertz. Uh, Compatibility issues.
মনে হয় স্যার।
Could be, sir. It could be.
এইটা তো বিশাল প্যারা হলো তাহলে, যে কন্টিনিউয়াসলি
কেমনে বার্স্ট করছে?
বার্স্ট করছে বলতে হচ্ছে হঠাৎ করে কারেন্ট চলে গেছিল, and typically the adapter that I have, it has an electronic circuit breaker within itself. Maybe that was not good enough for that thing. This my older monitor actually served me for a really long time. I used the older monitor for like 7 years. This is one of the first 2 millisecond response time monitors, Asus 228H black. I'm gonna have it. I'm not gonna throw it out yet. I plan to have it seen by some technicians. But my goodness. আচ্ছা, এমন হলে কেমনে ক্লাস নেব? দাঁড়াও দাঁড়াও দেখি এটা ঠিক করা যায় কিনা। I'm having 2 seconds blank, 2 seconds on, 2 seconds blank, 2 seconds on. So I resume the recording. So the other factor that we can have for the producing this curvature of earth thing is a large scale scenario. For localized air production or wind generation, another thing that plays a huge role is what we call the clouds, because whenever we have clouds in groups over a certain region, the places where we have thick clouds, they block the rays of the sun, so the land underneath the cloud remains cold, and the places where there is no cloud, those locations become hot. Remains the same mechanism like here. So you have heat supplied in one sort of surface area or the ground. You do not have that much surface heat supplied because the clouds are absorbing a significant portion of it. So in that case, the hot parts are gonna produce the hot current, losing their air is gonna go up because of the high temperature, and the cold current is gonna flow in from the cooler places horizontally to fill up that void. So that also happens. Together, these two factors actually produce the wind on Earth's surface. Important factor that although we have two factors which are highlighting over here is that the presence of the cloud is number 2 and the curvature of the earth is number 1. But you have to understand the 0 number factor, or the most important factor for this wind to be produced, was this supply of heat energy to begin with. If this supply of heat energy was not available to us, then the curvature of the earth or the presence of the cloud, they would not matter. Just because we have a continuous supply of heat energy from the sun, that's why these variations can give us the production of wind energy. So basically speaking, the point that I'm trying to make is that the kinetic energy, I don't know. I mean, randomly জিনিসপত্র কিছু change করছি and then it's working better. কি যেন বলছিলাম? Sorry. So the point I'm trying to make is that the heat, the energy that we get in the solar, in the wind energy form, this is also a very basic energy supply from the sun. One other thing, one other type of energy that we also have in our earth available, which is the wave energy. Wave energy means the wave that is produced in the, preferably in the oceans, because it is possible to capture energy from the wave. There are certain countries who have implemented pretty large plants which use some floater mechanisms which goes up and down as oceanic waves passes through them, and this going up and down will push in some liquid through a turbine and motor and generator, which will produce a small amount of electricity for every motion of up and down. And combining all of this electricity in a smart way can give us a large amount of electrical energy, and we can use it for our purpose. So this is just another way that by which we can produce the heavy electricity as well. But important stuff, the reason wave is created on water bodies, for example oceans or stuffs, is because whenever airflow happens adjacent to the water surface, that airflow starts to drag the adjacent water body. And you have to understand that air doesn't always flow as a laminar flow. Laminar flow means all the particles going in a parallel way, like the armies marching. Airflow essentially, if you consider multiple different particles of or molecules of air, they don't necessarily always flow in the same straight line. They actually have a little bit of random motion. Together, this is what we call the turbulent flow. This pulling effect of the air whenever it flows over a liquid surface or a water surface, that essentially produces the wave on ocean bodies and on large water or seas and large water bodies. That's the very important part. That's a very important part because sorry, it is that vibration. The energy of the kinetic energy of the air practically gets converted into kinetic energy of the waves. So this is just another expression of the energy available from the sun. If the sun didn't give us heat, wind wouldn't happen. If wind didn't happen, waves wouldn't happen. Done. The other type of energy that we, other type of renewable energy that we can have made available to us is what we can have from the tides. Do you guys know what the tides are? Like this, except for the washing powder.
So these are attraction between the waves of water and something.
Exactly, gravitational attraction between the two celestial bodies that is near to us. For example, sun and the moon. Moon being very close to us actually plays the larger role, but sun also adds a significant effect to it as well. Simply put, let's say if this is the earth, let me draw a different figure just to make it a bit more easier for you to comprehend. Maybe let's say this is the earth. Let me draw earth as brown. Let's say this is the earth. And just for the sake of understanding, figure not drawn to scale, consider that the earth is surrounded by some water. So let's say this is the water body that is around the earth. Okay. So this would be the shape of the water, where we have the same depth of water or same height of water level if the water level was not affected by any significant amount of mass, but that's not true. The thing is that we have moon. So what does the moon do? Is that, let's say, whenever the moon is around, it is always around, to be honest. Let's say I'm going to show the moon as maybe dark blue. So when the moon is over here, this produces a significant attraction force, gravitational attraction force onto this water. And this, I mean, I can explain logically and easily the half part of the water movement, but I cannot explain logically the other half part of the movement. The way, the gravitational pull of the moon affects the water body around the earth in such a way that whenever, because of the presence of the moon, this water shape would undergo some deformation, and that deformation would be somewhat like this. So I'm going to draw, let's say, purple, which is the deformed water body. Let's say this is going to look somewhat like this. Try to see if it makes sense. So water height would rise. So this would be the new water height. I really don't want to curve it, but actually if I do fill it up, then it will, actually I can try. I hope it somewhat makes sense. I hope it does somewhat make sense. So what I'm trying to show you is that because of the attraction of the moon, the water level rises on the closer part of the moon, and water level also rises on the opposite side of the moon. Now, why does the opposite side of the moon water actually gets a bigger height? I do not know this reason properly. I can actually study about this, but I did not, so I don't know this. But I should study about this. But I'm telling you that I don't know this thing because I don't know this thing. But this happens, and the other parts, for example, right over here and right over here, the water level gets lower. So this happens because of the attraction of the moon. Now, this is also a type of renewable energy, and the moon goes around our Earth every 24 hours, 24 hours or 12 hours. How often does the moon go around our Earth? So high tide, high tide, high tide. I think 24 hours. Do you guys know this thing? I forgot. No, 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 no. So the thing is, moon really does not go around the Earth really fast. Earth, it's on its own rotates pretty fast. So you see that the moon started over here, and multiple days have passed by. So the moon started from here. So 3 days passes by. Wait. So 1 day passes by. So the moon only moved from here to here. That's a very small distance. So 1 day passing by means that if we think for the perspective of Earth, for example, let's say I am located here. I'm located here. So within this 1 day duration, I have rotated around the Earth by 1 full 360 degree, which means for me, it would appear that moon would have moved around me from one horizon to the horizontal 1 full time, because practically I am stationary with respect to Earth, but the Earth is rotating around the moon. Hold on, anything boosts I'll say it again. Why do we see the sun coming out from the east and eventually going down on the west? Does the sun actually move, or the Earth, because of the Earth's movement, we are also moving? That's why our vision makes it so. What is the truth?
Sir, due to the Earth's movement, sir.
This is the Earth's movement. Practically, the sun is not moving. Practically, the sun is not moving at all. So it is the Earth's motion that causes us to see the sun go rise up in the east and going down on the west every day. So the same thing is happening over here. Earth is orbiting, or not orbiting. Earth is actually revolving on its own axis really, really fast compared to the motion of the moon. You can see that physically the moon have moved a very small time, and moon is going to complete 1 full cycle around the Earth in about 29.3 days or 27.7 days, which is called the lunar cycle. So that's how long it takes to rotate around the Earth. That's another thing. So approximately the duration. Why am I badgering your head about this? The reason is that I want you kids to understand that how often would we have tides, high tides and low tides on Earth? That's what I'm trying to get at. So you have to understand that within 1 day, the moon is going to travel this much direction around the Earth and eventually come up over here. That's basically what's going to happen. And maybe within that 1 day, this moon is going to travel from here to here, because it's going to take 29 days to cover this whole circle around the Earth. So approximately in 24 hours, the moon is gonna go around, for our viewpoint, the moon is gonna go around the earth, which means that this location will experience one high tide at this time. So let's say this is the position, this is the time where t equals to 0 hour. So let's say this is t equals to 0 hour. When the moon would eventually come over here at the bottom, I really don't want to zoom out. Okay, let's say when the moon has come up at the bottom, this would be t equals to 12 hours. So what has happened within these 12 hours? This high tide will always be close to the moon, which means when the moon was here, the high tide was here. As the moon traveled from here to here, this high tide came to here, and these locations, I mean, when the moon is right over here, let's say this is t equals to 6 hours. At this position, high tide would be available here, and low tides would be available here, which means this part would be have the higher level of the water, and this part would have the higher level of the water, and these two parts would have the lower level of the water. So this would be the low tide regions on the two equator side in with respect to the moon's position. So, so within 6 hours, any geographic location, if you consider this geographic location, or for example, let's say located with red, so any geographic location, every 6 hours it will experience high tide to low tide. So this is high tide right now when the moon was here. When the moon has traveled to here, it is now low tide. Now the moon is going to travel from here to here. Once again, this will be high tide. Moon is going to travel from here to here. T equals to, let's say, 18 hours. So that would be once again low tide, and then the moon is going to come up over here in t equals to 24 hours. That's one full cycle approximately, and then we're going to have high tide as well. So it means in one full 24 hours duration of time, any physical location on earth is going to experience high tide how many times? It's going to experience high tide twice and low tide twice. After every 6 hours, the water level is going to switch position. So let's say at one daytime hour, the water is at high. After 6 hours, it will be the lowest. Then after another 6 hours, it will be the highest. Then after another 6 hours, it will be lowest. So there is a cycle over here that we are having periodical supply of GP of water on a specific location on Earth. Periodical supply, and the period in this case is 12 hours. Every 12 hours, you're going to have one supply of GP. So your water level is going to rise to a very high level. So what we do, the way we can capture the tide energy. Tide energy capture mechanisms are not very popular because they cannot be they are not very they cannot be designed to be very useful, or we human beings still have other better options to capture energy. Easy to develop, easy to operate, easy to maintain, and easy to design and manufacture. So that's why capturing tide energy is not very popular, but there are prototypes and designs around the globe that we can start copying at any point if we want to. So that's why we are talking about this. The way the high tide energy works, there is a figure for this in our notes. Let me show you this. Thank you, sir. Hold on just a second. So this is the printer that we are using for this thing. This is how a tidal power station can work. This is, for example, let's say a creek, or not creek, essentially this is an ocean level where you have a certain small region through the ocean water or sea water can fall in. So we're going to produce a barrage. Barrage basically means this is actually kind of a dam where we can have locking mechanism. So we have two different sluice gates over here, which makes it a dam. So whenever the water will be at high tide, this is the high water mark. So at the highest high water mark, the entire region on the left and the right, the entire water will be going at this level. And at the low tide, the water level is going to fall to this value. So this is the low water mark when the there will be low tide. So these two level variation is going to happen 6 hours at 6 hour difference. So what we are going to do, we're going to allow the water to pass through. We're going to open up both of the sluice gates and allow the water to pass through in the high tide region. And we're going to lock up the water over here. When the water has reached the maximum level, then we're going to close these gates to lock up this water over here. And then we're going to wait for the 6 hour duration. Within the next 6 hours, this water level over here, the seawater, which is being affected by the moon. This water is also affected by the moon. The reason this water cannot flow out because we are not allowing it to flow out because we have locked up this water by the help of some barrage and some sluice gate mechanisms. So we have practically encapsulated or hold this. We are holding this water. So after 6 hours, this water level is going to fall down. Now you can see that compared to this water level we have a bit of a H. We have a bit of a height variation, and this height variation is basically what is going to work as our GP storage. So when this water level will go to the very bottom, then we're going to open up these things and we're going to allow this water to pass through some turbine, which is going to be placed over here. So as the water will be drained from here to here, this turbine is going to rotate and we can capture some portion, not essentially all of them, because there is nothing that is 100% efficient. We can convert the GP of the water, which is going to convert into K as it's going to flow down through the sluice gates, and that K can be converted into the turbine and in the subsequent generator as electrical energy. And then we are done doing it after the 6 hours. Then we have to wait another 6 hours for the water level to rise when the sluice gates will be all open. And then after another 6 hours, which means at 12-hour mark, there'll be high tide. So when the water will be once again rise over here, we're going to close this thing. And this will going to cycle every day. So we're going to lock the water at the high tide region, and we're going to allow the water to, we're going to do the energy conversion, or we're going to produce electricity during the low tide duration. So every day in a 24-hour duration, we can only produce energy out of a mechanism like this twice. Beauty of this thing is that this is always going to be available. As long as you have water flow, you'll always have it. This is not dependent on the daylight period. For example, solar energy largely depends upon the availability of sun, and the clouds not present, and storms are not happening. So the brighter the sun's energy flow onto the surface, the better is the production of solar panels. So it only works on the day. It doesn't work on the night. Wind energy is also a bit unreliable because you need, we can essentially not precisely predict the direction of the wind flow, but there is a certain observational or statistical data that we can develop for a certain region of Earth, where that in which direction the wind flow over here for the entire 12 months duration of the year, and we can profile that up and set up our wind turbines along that profiling. But that can also vary sometime. But the beauty of the tidal power is that these variables are not applicable for tidal power, because moon is always going to go around, and whether the sun is present or not, this is the important bit. If we somehow lose the sun and if we still have the moon, let's say Earth and moon is there, and moon is going around the Earth and sun is not present anymore, so the gravitational pull of the moon and the because of the presence of the water, we can still generate energy out of this mechanism. So this is a very important thing. If you wonder why is it such an important thing, or in other sense, why are we so interested about this thing? Here's the deal: the rate of energy that we humans experience, or we humans enjoy on Earth, is quite high compared to the other planets which are further away from the sun compared to Earth. For example, if you sorry, if you think about the sequence of the sun of the planets, we have the closest is the Mercury, Venus, Earth, then Mars, then we have the entire asteroid belt, then we have the Jupiter, Saturn, Uranus, and Neptune and Pluto. Pluto is a bit questionable, but let's say Pluto is still there. So the further the planets are, the less amount of energy from the sun actually incident upon those planets, because the sun's energy, which is radiated from the center of the solar system, it's actually spreading out in three-dimensional spherical shape. So the further you go out, you have less and less intensity of that energy flow. So if we consider from a really far away location of a planet, if we don't have enough supply of solar energy, but if somehow that those planets have some satellite, natural satellite like a moon, and there is water in that planet, this type of design of energy generation can prove to be more efficient and more yielding, more energy converting mechanism for those environments outside the Earth. So because we are pretty close compared to other planets of the solar system, we are pretty close to the sun. That's why we are not very much interested about this, because we have other sources of energy flow to Earth pretty abundant. Light energy, heat energy, which is converted to wind energy and then wave energy and subsequent other forms. So we also have we are digging up the ground to liberate fossil fuel. We have found out nuclear fuel. So we have a lot of other options. But places where we cannot initially achieve these options, but if we can utilize the gravitational pull of the satellites, natural satellites, then we can utilize this design very efficiently. So that's one of the reasons that why tidal power is still discussed to everyone, because although it is not very popular for Earth environment, but might as well be very useful for other places where the solar energy is not as abundant as it is on Earth. এই পর্যন্ত বুঝা গেছে কিনা? Hello?
Yes, sir.
ওয়েভ এনার্জি অ্যাকচুয়ালি অনেকগুলো ডিফারেন্ট ফর্ম আছে। এইখানে আমাদের ওয়েভ এনার্জি একটা ফর্ম দেওয়া আছে হচ্ছে which is working by air, that we are producing some sort of a falling cavity thing over here. So when the waves are coming in, the water level is going to rise up. So this water is going to push the air in this way. So this turbine is going to rotate. We can capture that energy. When the wave is going to fall down, then water level will suck the air. So then the air is going to flow through this pathway. This will also rotate the turbine in the opposite direction, but we can design the turbine to produce energy for both of this motion, forward or backward. As long as the turbine is rotating, no matter what, it can produce electricity. We can design it like this. Is just one design. The other common typical design that we can have for wave energy, let me just show you some way that which can make some better sense. There it is. Well, I can actually start up the video. Okay, I will. So let's have a look. Not very big, so have a look. Now, they've used this term that there is one source which is more reliable than solar energy and windmills. More reliable means that it is affected by less uncertainty. Solar energy has the uncertainty because of the clouds, and you do not have it for half of the day. Wind energy is unreliable because of the uneven heating. So these two energy sources are available to us, but they are not very reliable. But wave energy is reliable, because if you set up a wave energy source at a certain part of the ocean, you're going to have waves happening 24/7, period. So you can have continuous power output from there, continuously, 24 hours a day, 12 months a year. You're going to have power out of it. So that's why they're using the term reliable, which means suddenly those wave power stations are not going to stop working like solar panel electric station, or like a wind powered electricity generation farm. Exactly, this is what we want to see. So these are the floaters. The floaters are actually going up and down, and these are the levers you can see over here, which are actually connected to some revolving parts over here. So it's very much similar. It's very much similar to what happens in a bicycle. So we pedal down on the bicycle by applying a force in one direction, and then do you kids know the working of one-way wrench? Because I forgot the name of this thing. পরে দেখা যাবে। আগে এটা দেখে নাও। আচ্ছা এটা পুরোটা শেষ হোক তারপর আমি আলাপ করতেছি। দেখো exactly. This is what I was talking about. Have a look. As this thing is going up and down, this is just one of the examples for the conversion mechanism, but there can be other different designs as well. Here, what they are doing, they are making this vertical arm, which is going around this gear, and that is producing some electricity over here. So every single time is going up and down. There is some motion over here, and this alternator will be producing electricity out of this thing, and we can accumulate those electricity by appropriate electrical circuit designs, and then we can conserve it all together, convert that into the 220 volt, which is because we have to convert it into 220 volt AC for us to be feed it to the national grid, for it to be made available to for the customers, because the national grid or the grid means the whole electricity network is operated at 220 volt. So this is just one example for how this thing works. This is beautiful. Let's have a look at it again. This is another beauty of it. I mean, you just make one of these things in appropriate place close to the shore, and if you allow enough gaps underneath this structure, you can actually attach floaters on both sides, basically doubling your production. That video, I'm gonna keep this link so that I can credit them so that I don't forget. এটা হচ্ছে wave. বুঝা গেছে কি প্রসেসটা কিভাবে কালেক্ট হচ্ছে? Did you understand this part? মানে what is the underlying principle here? এই পার্টটা কি বুঝা গেছে? হ্যালো, আমার কথা শোনা যাচ্ছে না? We have a chat option. আচ্ছা, okay, so that's one way. I'm actually personally very interested to show you kids a lot of the other designs the scientists are working around the world to make sustainable energy or renewable energy more available for us human beings, because it is really, 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 really important. So another design that I'm going to show you right now, because I want you kids to have a look at it, which is the solar thermal power. I'm going to, okay, I might as well keep the recording on. এটা হচ্ছে দাঁড়াও, this is one of the mechanism for solar thermal power, that we have a lot of reflectors which actually accumulates the heat of the sun, pretty much like a concave mirror, to a certain location, and that heats up some liquid over here which boils the water, and then we run that water into this thing. So this is actually particularly one of the this thing that you can see over here is particularly one of the plants that has always been in function, that they have made this kind of a array. All of these things are focusing the sun's energy to the top of this central pole. Here is another view of the same thing. But I was looking for the convection power plant, which is really, really, really interesting. No, they are all reflectors. I don't see the convection. Okay, so I forgot the name of this thing. Environment, yes. This is just an animation, but this is amazing. Hold up. No, we don't need that kind of music. That's it, 240p. আচ্ছা, 240p দেখো আপাতত, বুঝা যাবে। This is chimney. And some corner of the screen, there will be a temperature reading. You really need to see the temperature value of this thing. So this is the mechanism. So what is happening? The sun is giving us the heat. The heat is getting absorbed within this ground panel, which is like working like a greenhouse, and that air, hot air, is pushed in by a little bit of gradient of this canopy, the transparent layer, which can be made from plastic, very cheap plastic, and that air is going to be pushed towards this thing, so that there will be high air pressure over here. So there is one thing that you could do. You could place large wind turbines in these places, which is going to require a really large amount of turbine. Other than that, what they designed, they placed radial turbines on the inlet sides and allowing this thing to go up. So the ground air temperature is about 86 degrees Fahrenheit. At this part where it is most concentrated, the air, it has the most amount of volume compression. We have a really high temperature, 158 degrees Fahrenheit. And then as the air is going up, it is once again cooling down as it is coming out of the head of the chimney, because the upper layer of the atmosphere is cooler. So this is the location where we are essentially extracting the energy, heat energy of the air, into converting into kinetic energy of the turbine. Turbines eventually rotate the generators, and that's basically how it works. Size comparison. Have a look at the temperature at the bottom right corner and see the possible animation of the temperature. This is where the temperature is almost fixed. At the turbine, the temperature starts to decrease because that's why we absorb energy. As we are now slowly going up, the temperature of the air is slowly decreasing. These radial structures are structural components to make the tower hold steady. One of these circular thing can produce up to 200 megawatts, and they are planning to commission 5 of those in certain part of France, I believe, or Belgium, I think. Did it make sense? Oh, Nuran, you just say that you cannot hear me over the noise of the video. Achha, I'm so sorry. But okay, I'll help you explain better. But did you understand what was happening here?
Yes, sir.
You might feel like this is redundant. I personally am very interested to show kids how different type of energy conversions are happening, because these are the burning requirements for us human beings to produce sustainable energy solutions, which is pragmatic and also useful. Currently, these convection type of design is a bit down the line. We are not we human beings are not very much using it, because apparently the reflection mechanism has taken over at a much higher part. So that's that for the energy conversion processes, and that's basically what I had to say about this whole PDF, which is available to you. Do you have this PDF attached to your notes? I mean, in your actual booklet, printed booklet. Do you have it?
Yes, sir.
So,
You don't have it. Did I share this with you in the messenger group?
yes.
Achha, so you can essentially download this, have it in your software environment, and anytime you need to get a go through this one, you can have a look at it. Actually, it would have been better if I gave you a PDF printout for this one. এটা হচ্ছে Edexcel IGCC book, which has a cover like this. That book is essentially not very well for a lot of chapters, but this chapter was very well written. For example, this thing over here, this is actually from another chapter. This is, if you can see that the page number will be different. This finishes at 155, and then we have 156, and then we have 157, and then we have suddenly 100. Oh, no, hold up. Gotcha. No, this is a continuous chapter. So what they have shown us over in this chapter is that how can we have a better energy conversion. So this is one way how the solar panels work, how solar collectors work for small scale. We also have questions about this thing. So I'm going to discuss the function of this device. This is basically what we call a solar collector. Do you kids understand the greenhouse effect? Do greenhouse need to be green? Anyone?
No,
Well, you do not understand, or greenhouse don't need to be green. Which one is it?
they don't need to be green.
They don't need to be green. Exactly. Greenhouses are basically made up with some sort of transparent material. It can be glass, it can be plastic, it can be polyurethane, it can be polycarbonate, something. Whenever the sun's ray, the basic mechanism, and you can see a lot of animation about this thing if you look up in the YouTube. I'll leave that to your hands. But the idea is very simple. Just because I'm going through this, I'm going to show you. Let's say this is a house. We can draw a very nice house. Let's say this is a house, which we want to use as a greenhouse. So what we're going to do, we're going to make these, at least the tops or the roofs, with transparent materials. The property of the heat waves or infrared waves is that whenever the infrared waves which are coming from the sun, they have a pretty small wavelength. So their wavelengths are really small, which is the wavelength. They can penetrate very easily through this glass material. And eventually, whatever that is inside the greenhouse, the soil, the air, the plants, if you want to have some plants, or if you want to have some people inside, the people, everything that is inside this thing, these infrared rays would essentially get absorbed. Let's say here I'm placing a human being over here, stickman with hair and eyes and whatever. So this person is going to absorb the small wavelength infrared waves, and then he's going to radiate these heat energy from his skin as well. But interestingly, when he's going to radiate these rays, they are going to be radiated at a much longer wavelength. So now the waves have become a bit longer in wavelength. The actual inherent reason or what the atomic level explanation is not required for you. What there is a key factor which controls the size of the wavelength from hot bodies whenever they undergo radiation, and that key factor happens to be temperature. The sun operates at a really high temperature, like is really high temperature. So hot objects tend to give out infrareds at a much smaller wavelength, and low temperature objects tend to give out infrared at a much higher wavelength. So because our bodies or earthly temperatures are significantly lower than the sun's temperature, that's why the energy that we are going to radiate from our body or our heat sources, that's gonna have a much longer wavelength. The property of this glass material, which is located on the roof, or maybe the entire body of the greenhouse is made up from glass, is that it is going to allow the small wavelength infrared waves, but it is not going to allow the passing of the large wavelength infrared waves. So as a result, these large wavelength infrared waves are going to reflect it off the boundary, and they're going to bounce back and forth. So you are basically producing like a one-way mechanism for the heat energy. So you're allowing the heat to enter, but you're not allowing the heat to dissipate out in terms of radiation. This basically allows, when there is in the day period, the inside of the greenhouse to slowly start to heat up, warm up, and that's how we can store energy. So that's the idea for basic greenhouse effect. So bottom line, to achieve greenhouse effect, you need to have some sort of a plastic or transparent material. That can be glass, that can be acrylic, that can be polyurethane, that can be polycarbonate. It depends upon the molecular structure of this thing. They can have different names, but you need to have some sort of plastic transparent material which is going to allow the sun's infrared rays to pass in, but it's not going to allow the radiated heat energy to go out. So that's the basic idea for greenhouse effect, and that's how greenhouse works. So this is not greenhouse effect. This is the greenhouse mechanism. Greenhouse effect is applicable for the atmosphere, where the carbon dioxide gas works like a greenhouse layer and doesn't allow the earth to radiate most of its absorbed energy. And so that's essentially what is making the average temperature of the atmosphere and for the entire atmosphere slowly go higher up, causing what the polar ice caps melting and so many other problems. However, that's a different issue, but let's have a look over here. Here, this black thing that you can see is basically painted black so that they would absorb more heat energy. The top is made up of glass to trap an air layer. So light from the sun is going to go in, is going to penetrate through over here, and this black thing that you can see, it is actually have a look. Copper water pipes with matte black surface brazed to a sheet of copper with matte black surface. So let me tell you what it means by brazed. Brazed means it is welded. It is welded. So we have copper plate and we have copper tubes which are welded onto this thing. These ring structure that you can see, this is the cross-sectional view of the whole thing. The entire structure, actually, I think I can find a good view of this thing maybe in the worksheet. Hold up. In the P2 worksheet, we might have a good image for that. We might. Work energy power. This is kinematics, elasticity, work energy power, dam, jumping, headlight, motor base plate. Maybe on the composite. Do we have it on the composite? Come on. Last problem. Okay, it's not in here, but there is a certain very good image for the, let me just show you. Hold up, give me some time. Images. Not vacuum tube. This image can really help, but yes. Okay, yeah, this is a pretty good image that can serve our requirement. So what this is showing us different section views for this thing. So what they're trying to show you over here is that we are going to have a copper plate because copper is a good conductor of heat, and on top of the copper plate we're going to have copper tubes which are going to be zigzagged in this spiral shape at some gap. The measurement of how much gap should you have is a subject to experiment and repetition, but that's the basic structure. This whole thing of copper plate, and on top of the copper plate we have the welded copper tubes. This entire thing will be painted in matte black color because matte black color has the biggest capability to absorb radiation, not to reflect, not to bounce off, rather to absorb the radiation heat. Above this whole structure, we're going to have a glass layer. So this thing that you can see, which is a bit light in color, this is our glass structure. So this glass structure is over there to trap the heat and eventually produce a greenhouse effect. You have to understand that we are using this thing in a cold environment. Let's say in the cold countries where the temperature of the air is, let's say, slightly over 0 degrees Celsius, let's say 2, 3, 4, 5 degrees Celsius. I'm saying slightly over because for this whole thing to work, we need to have liquid water inside the tubes. Ice inside the tubes would not help us. So that's why I'm saying it has to be above 0 degrees Celsius. So, but we want to capture, so the entire air that is around this whole thing is actually pretty cold, but we want heat to be absorbed by these copper tubes. So the environment around the copper tubes has to be warm. That's why we are placing this glass structure, glass boundary, so that we can produce a small greenhouse effect within this trapped air. So it is going to come in, and it is going to get absorbed in this copper tube. And within this copper tube, we're going to have two different inlets. So we're going to allow cold air from the lower side. This is designed to be placed on a rooftop, so there will be some angle. So we're going to feed in cold water from the bottom. And as the water is going to become hot, necessarily it's going to start to rise up because of convection current. Or we can have some motor as well if you want to have better efficiency. But then again, running the motor would cost you energy. So we might as well rely upon convection water heating. So this water, which is going to run inside the tube. So this is actually the full sectional view. And on the PDF that we are discussing, we have the cross-sectional view. So you are basically seeing a cross-sectional view of this whole thing, where these are the cross-sections of the tubes. And inside these tubes, inside this hole, we're going to have flowing water. So this water is going to absorb the heat from the environment, from this environment. And we have on the bottom, we have some thermal insulation so that this copper tube does not lose heat to the atmosphere. This is pretty important. We have to have thermal insulation because we want the what is our aim? Our aim is that whatever the amount of heat energy that will be absorbed by this device should be transferred into the water that is flowing through these tubes. That's what we want. We don't want the absorbed heat to be leaked out from this whole contraption that we are making. But then again, we cannot essentially stop it by 100%, but we can significantly minimize the heat loss because significantly minimize the heat loss by introducing some lagging material. It can be some sort of foam, some sort of polystyrene material, or যে শোলাগুলাকে যেন কি বলে styrofoam, exactly. We can have some sort of styrofoam stuffs, something that is fluffy and light material, which is a good insulator for heat. So we can use those stuffs over here, and that's basically helps us to prevent the heat loss. So what the way it's going to work is that we're going to feed cold water over here. Water is going to absorb energy, and because of the convection, water is going to slowly travel like this spiral way. It's going to go travel up, and immediately on the top outlet, we're going to have hot water coming out. So we're feeding cold water in. By this contraption, we are making the water heated up. So this is working only by absorbing the free energy available from the sun. This is working because we have designed this device to trap the heat energy and provide enough temperature to this whole absorbing mechanism, the copper plate, copper tube, and the water inside, so that they could capture that heat. If you would not have this mechanism, you would just place a bucket of water in the sunlight, under the sunlight, this thing would not work, because that water would be exposed to the normal room atmospheric temperature. You would not have any greenhouse effect, and you would have evaporation, so you'll be losing heat anyway. So this would not work for an open mechanism. This can only work for a closed mechanism, which we are producing over here by using the whole mechanism, and also by greenhouse effect by the glass panel, which also really helps. So that's the idea of a solar heater. If you wonder that how does that help, or how much of a temperature of hot water can we get? Well, as long as this hot water is comfortably hot, it is a good supply of heat and a good supply of energy source. Because in the cold countries, a huge amount of energy is used for the comfort of human beings, to keep the inside of the houses warm, to keep the running water warm enough so that lifestyle values are higher. It's difficult to work with really cold water. We don't feel comfortable to take a shower or a splash or cooking or stuffs. I mean, if you really want to cook something, you have to increase the temperature of the water to the boiling point. So heating up water, is a pretty large energy consumption, energy usage location or part in the cold countries. So having the temperature of the water increase by some amount actually helps a lot. And if you, the more of these things you can stack up on your roof, provided that your roof is not shaded by bigger trees or anything else, and you are having direct sunlight falling on your roof, we can actually significantly absorb a significant amount of solar energy by this thing. These are called solar collectors because they collect the sun's energy. That's just the name. বুঝা গেছে কি এই জিনিসটা, মানে অপারেশনটা বুঝা গেছে সবার?
Yes, sir.
কনভেকশন কারেন্টের পার্টটা বুঝছো? যে আমরা নিচে থেকে এখানে কোল্ড ওয়াটার দিচ্ছি, এটা কি বুঝছো? মানে উপর থেকে এখানে কোল্ড ওয়াটার দিচ্ছি না, এটা কি বুঝছো?
Sir, could you repeat that part?
Exactly, because whenever we heat up some fluid, it expands in volume, which means its density goes lower, which means it tends to flow upwards. Now that upward flow could happen in a beaker, that upward flow could happen in a pipe as well. Here, that fluid flow is going to happen in the pipe. So we're going to feed the cold water from the bottom. So that as the water heats up, naturally it will push the water to the upward direction, so that it will be easier for us to get the hot water on the outlet side. We don't have to use pumps. The heat energy stored within the water will work as a natural pumping mechanism. Bucho?
Yes, sir.
So, but in other case, we could also do this. We could also feed cold water from the top and allow the gravity of the gravitational pull of the water to actually run down this tube and eventually take the hot water out. There can be also some sort of design, but individual designs of the panel has their individual pros and cons. I just told you the typical design aspect that we usually go by putting in cold water from the bottom. That is the most common design, because in that case, we don't have to essentially pump the water. The solar heating basically is responsible to move the water from cold to hot region, which makes it more efficient in terms of energy consumption. So that's that. It's 7:32, so I'm gonna stop today's class because I have to start a new one, and you might have to leave. Next class, I'm gonna start discussing the worksheet paper. So multiple MCQ questions and paper 2 questions. If you have already attended those questions, well, thank you very much. If you haven't, you might as well try something. I'm gonna start the MCQ paper first, and then I'm gonna go for the paper 2. So yeah, and this will be on Friday. Friday. Do you have a next class on Friday or Thursday?
Friday.
Sir, Friday.
Yes, so we're gonna have our next class on Friday. I mean, last class class because last class আমি খুব অসুস্থ ছিলাম, and I actually went through a whole series of medication. Looking forward to it. তোমরা পারলে সময় পাইলে এটা ট্রাই করো। আমাদের কি আগে কোনো ওয়ার্কশিট সলভ করা বাকি আছে? Like, is there any worksheet that we did start but did not finish to the end? আমরা মোমেন্টের ওয়ার্কশিটগুলো পুরোপুরি শেষ করছিলাম না?
Yes.
Brother sister problem. So momentum power chapter is work energy power. So I don't think there is anything left. Okay, if anything is left, we can also discuss in the next class. Ask me to do that. And Asif, if you want to picture to DMD course, I'm dekbo, and I'll get back to you on Messenger later on. Okay, sir? Okay. Thank you, kids. Allah Hafiz.
Assalamu alaikum, sir.
Walaikum assalam.
Assalamu alaikum, sir.
Walaikum assalam.